All right, so yes, thank you. I know. So we'll jump into chapter, what is this? Chapter 8 now. Um, on Wednesday in class, you learned a little bit about both sections, 8.1 and 8.2, vectors and plotting in 3D. I don't know if we'll see. I think I can get this started on vectors, but I don't want to rush this part too much because where we're transitioning to now a little bit, this is a preview for 17C where we basically repeat some of the same ideas in 3 dimensions, which is, the real world is 3D, right? We've been practicing calculus for 2-dimensional functions, but the world is 3D. And actually in 17C, we consider like more than just 3D. Like you could have functions of more than, you could have, functions of 3 or 4 or 5 variables. You can't graph them because we can only graph in 3 dimensions. That's our highest, but we can certainly imagine functions like that. So we learn about vectors in chapter 8, 3 dimensions, and then we actually learn about matrices. So this is where 17B takes a big turn. If you've got friends in 16B or 21B, we're going to get into vectors and matrices. They don't do that in those other courses, until, at least in the 21 series, until later on. And some of the stuff we learn with matrices, we will use in 17C. I'm doing that right now with my 17C class. So anyhow, let's start about 3 dimensions, talking about 3 dimensions. And the first change you may have noticed right off the bat is if I'm asked to plot a point, which you would have X, Y, and Z in that order, we're used to X going left and right and Y going up and down. But now that we're adding a 3rd dimension, we're going to have X coming in and out of the paper. The origin's right here, and you do have a negative X going backwards into the paper. You do have a negative Y going this way and a negative Z. But the points we're plotting here are all positive, 2, 4, 6. So positive X is coming out towards you, Y is going to the right, and now Z is going up. So to plot the point 2, 4, 6, just imagine you're at the origin. You're going to take 2 steps in the X direction. And then 1, 2, 3, 4 steps in the Y direction. But you have to realize that if you walk this way and go four steps, that's not going to take you directly underneath the 4 like we're used to seeing. There's this whole 3-dimensional perspective, right? 4 units right from here is going to put me about right there. So I'm going 4 units this way. And then I'm going to go up 6 units from here. Similarly, that's not going to take me even with 1, 2, 3, 4, 5. If I put 6 on the z-axis, it's not going to take me up even with it like we're used to seeing with 2-dimensional graphs. The idea is this distance from here will only take me to about maybe right here. Right, this is 6 units up from this point. So this would be the point 2, 4, 6. Now, you're probably not going to be plotting on a test or anything anytime soon because, you could obviously just put a dot, kind of estimate, not draw these lines, put a dot and call it 2, 4, 6. Nobody can really dispute that you haven't plotted that correctly. But more about what we're doing here is that practicing plotting and graphing things in 3D is going to help us to visualize what's going on, particularly when we get into 17C and we start studying things in 3 dimensions. Okay, so don't worry if your graphing skills aren't up to par. But, for your notes and everything, to make this look more 3-dimensional, one thing you can do is dress this up a little bit. Let me show you what I mean. Give me a second. See what I've done here is just by adding some extra lines here, it really helps bring out that three-dimensional perspective where you can think of 2, 4, 6 as the opposite corner of a box where the origin is the other corner, right? That's the one opposite that. And just by adding some lines, it kind of makes it feel more three-dimensional. Okay. Well, I can draw. What's funny is I can draw some three-dimensional graphs because I do this all day long, but I'm a terrible artist, especially trying to draw something three dimensions. Like, when I play Pictionary, I draw stick figures. I can't draw very well, but I can do these graphs. I don't know why. Okay, some terminology now that we want to get familiar with. Are the three coordinate planes. I could actually use this box to actually illustrate that. If you think of, well, I'll just draw it on here. I'll draw a new set of it. A plane is a flat surface, right? Like the table you're writing on is a plane. It's a flat surface. Now your table has endpoints, right? A plane, just like a line, would go in all directions indefinitely. But usually if someone wants to denote a plane, they might draw like a rectangle. That's part of a flat surface here. And the plane that I've drawn here, if you think about it, every single point here is, you don't go up or down, right? You go move over X, move over Y, but you don't go up or down. So one equation for this plane, we could call this the plane Z equals 0. But another way we can describe this plane is you can think of that as the plane that's kind of made up of just the X and Y axis. There's no Z involved. So we often refer to this as the XY plane. XY plane. And a good way to visualize this, I've always taught it this way, and our book actually is the first book I've seen that actually presents this way. A good way to visualize in 3D is whatever room you're sitting in, look at the corner of one of your corners of your room. Think of this as the floor, right? This is the floor of your room. And you would have a wall over here and a wall over here, and those are also planes. So let me this vertical plane right here, I have two ways I could describe that. That is a plane that's made up of the X and Z axes. There's no Y movement, so I could refer to this as the XZ plane. Or any point on this plane, you don't move left or right, I could also call that Y equals 0. I'll put parentheses, either one. Okay. And again, just to note that these planes do go in all directions indefinitely. You could put like arrows to kind of, it's not just a rectangle, right? It's the whole, it goes on forever. Whatever. Okay, and then the back wall over here, let's see, do I have another color that might be distinguishable? I don't know if this will show up, but this is a pink. Is that any different? Oh, here, this is a cool color. Here's a light blue. This plane right here, the back wall, is the YZ plane. Otherwise known as X equals 0. So you'll often hear referring to the XY plane. Okay, so like some of the questions I'm just in chapter 8.1 that I've seen are really not hard if you just imagine the graph. Like, for example, now that you know what those coordinate planes are, if I went back here and I asked you, how far is this point from the XY plane? we know that the XY plane is like the bottom of this box, right? It's the bottom of this box. That's the XY plane. So how far is this point 246 from it? Well, how did I get there? I went 2, 4. I'm still in the XY plane, but then I went straight up 6 units. So just by graphing it, you can hopefully see that it's 6. It's 6 units, right? What if I said, just for one more, how far from the XZ plane? What would you say? Yeah, that's just 4 units. The XZ plane was back here. And so think about how we got to this point. We did go 2 here. We went 4 over, so we were 4 units, and then we went straight up. So we're still 4 units, right? That's still 4 units from the XZ plane. So this would equal 4. What else could I? Okay, I could ask, might as well do this. Might as well do this because I know this is coming up. What if I said from the origin? From the origin would be like the distance. Do I have another color? Purple. Let's see if that works. That's the straight distance from here to here. And the way that works, got a lot to get through, so I'm not gonna try to prove this or show it, but you could show it by doing a couple of triangles here and doing the Pythagorean theorem. Your distance formula in 3D, I saw this in the lecture notes. You know how the distance formula in terms of just X and Y is like, X2 minus X1 squared plus Y2 minus Y1 squared, square root of that. If it's just an extension of it. So if you have a Z, it would be Z2 minus Z1 squared. That's your distance formula in 3D. So for us, the origin is 0, 0, 0. So it's going to be easy. It's going to be 2 minus 0 squared, 4 minus 0 squared, 6 minus 0 squared. My distance is 4 plus 16 is 20 plus 36. So it's the square root of 56 units from the origin. Okay, I got to move this up here to get to my next question. Yeah, I can kind of fit that in. There we go. Okay, so in more terminology, in 2 dimensions, you've been working with this for a long time. You're probably already familiar with your 4 quadrants, right? 1, 2, 3, 4. But in 3D, if you think about, remember my analogy of the origin being like the corner of a room. Let me use this as my picture. Imagine you were in a multi-story building, okay? And you're in the interior of the building. You're not at the end where maybe the windows are or whatever, right? How many rooms on this floor, if you were up on the, let's say the 2nd floor of a building, and you're in this room right here, you're in, over here, here, you're somewhere in this room, but there would be 4 rooms on this floor that would share the origin, right? One behind this wall, one behind the green wall, and one like diagonal here, right? Now, if you went downstairs on the 1st floor, how many rooms would look up and see that same exact point? Do you see that there's 4 rooms underneath? And so if you put those all together, how many rooms share the origin? There's 8 of them. And so in 3D, we talk about 8. And if instead of quadrants, we call these octants. 8 octants. Okay. Now here's the deal with octants. If somebody asked me, where is this Grant, where is the sixth octant? I have no clue. I don't know how they're oriented past number one because, and the only one you really need to be familiar with is the first octant. And just like the first quadrant, where X and Y are positive, the first octant is when X, Y, and Z are all positive. So that point we sketched where we did 2, 4, 6, that was in the first octant. Okay. First octant. And to show you why this matters is soon, if not this quarter, certainly next quarter, they might start a problem by saying, consider the part of a sphere that's in the first octant. And you need to know what that means. It's kind of like saying this: if I wanted to graph a circle, but only in quadrant one, and we're used to seeing that as a quarter circle here, right? But imagine you had a sphere centered at the origin and you only wanted the part of the sphere that's in the first octant. It would look something like this. You would go down like this, down like this, down like this. It would be, I don't know if you can tell what that is, but it's going to be 1/8 of an entire, like if I sketched an entire sphere, maybe I should have done it that way. It would only be like just 1/4 of it. It would be like this, this, straight down the back in the middle, and then around here. See that? So there'll be times when we refer to a portion of a graph that only in the first octant, that's what they mean, only when X, Y, and Z are positive. Speaking of graphs, let's graph. In this section, we kind of take it slowly in 3D. We just work with planes and spheres, as you've seen, mostly planes and spheres. So if I want to graph y equals 4, we know in 2D, this is just a line, right? This is a horizontal line. And how do we get that? How do we graph that line? Well, one way to think about it is I draw my XY axis. If y equals 4, that means I go up to the y axis at 4. And I know it's a horizontal line, but another way to think about it is if y equals 4, it doesn't matter what x equals, y is always 4. So it's like just extending this parallel to the x-axis. That's basically saying no matter what x is, y is always 4, right? The way we do this in 3D is kind of similar. We go to the y-axis at 4, 1, 2, 3, 4. So here's 4. So we have this point. And in the same idea here, if y equals 4, let me write this underneath. What that means is, what they're implying here is x and z can equal anything, right? No matter what x and z are, y is always going to be 4. What that essentially means is you could envision this graph as you have y equals 4. That means you could extend it in the x direction. I want to go parallel to the x-axis, right? Any point along here has a y value of 4, and I can extend this in the z direction too. I can go straight up as far as I want. And if you consider all points that look like this, where you extend it, let me see. I want to make this straight up. I want this line. So some tips I've learned with three-dimensional graphs: when I connect this end, I want it to be parallel to the x-axis, otherwise it's not going to look right. Kind of close. So do you see what is actually in reality? This is maybe it helps if I tie it back to the XZ plane. fact, you might see this. Actually, this was part of my original sketch here. Do you see that this is like the vertical side of my box that I had before, right? And so in 3D, y equals 4 is actually, we would describe this as a vertical plane. And it does go in all directions. It goes backwards that way. It's a vertical plane. So when we see just y equals a number or z equals a number or x equals a number, it's going to be a plane now, not a line that we're used to seeing in 2D. Z equals 6 would be same idea. I would go to the z-axis at 6. Let's just pretend this is 6 right here. And what that means is it's whatever your x and y are, z is always 6. So you could imagine going some distance in the y direction, a certain distance, and in the x direction, a certain distance. How far you go is totally up to you. But hopefully you're seeing, maybe if I do the same thing I did with the other one, if I do you see that as a horizontal plane? Now, what if I was asked to describe what does y equals 4 comma z equals 6 look like? Well, what I would be looking for are points that satisfy both of these. Let me re-sketch it. So here, let's say this is y equals 4. Because we know from what we just graphed before, y equals 4 is a vertical plane like this, which at some point is going to intersect the horizontal plane z equals 6. And what we would be thinking about is, what are all the points that satisfy both of these? Points lying on both planes. What would you describe that as? How many people see a line, right? Lie on a line, are a line in this case. That's a line in three-dimensional space, a line coming in and out of the paper. Let's do one more plane, I guess. And so one of the things I'm wanting to, the concepts I'm wanting to emphasize here is, as you saw, the way to think of a plane, I'll go back to this, I guess, is, z equals 6, you go to the z-axis, and if x and y are not there, that means you extend it in the x direction, you extend it in the y direction, and that's going to generate a flat surface. So here, my equation x plus y equals 4, that looks like a line to me in 2D, but because there's no z in this equation, what I want to be thinking to myself is z can be anything, any number. I just have to make sure that x plus y equals 4. And so how I can imagine this graph is just like if I was graphing lines, I could find my x-intercept, for example, when y is 0, x is 4. So I know it hits the x-axis at 4. When x is 0, y is 4. I know that any point along this line in the xy plane satisfies that, right? Just like you're plotting a line. Once you have 2 points, just connect them with a line. But this right here is a line where z is equal to 0 because I'm in the xy plane. But if z can be anything, what that kind of means is you could imagine this line lifting it upward and downward, stretching it out. It's actually going to look like, let's see. So I'm going to stretch it vertically. This time, maybe I'll do this just to really give it a three-dimensional feel. Do you see this as it's still a vertical plane, but kind of at an angle through here? And of course it does go in all dimensions, right? It's extending. So what am I sketching? I'm sketching the portion of this plane that is in the first octant, right? That once I stop right here, it's going into the negative x direction, and same thing over here. It's going into the negative y direction. This is going down. So I'm just looking at the portion in the first octant. So maybe here what I'll put is graph x plus y equals 4, z equals 0, then extend, or sometimes we call it stretch, the line up and down to get a plane. All right, so that's kind of one idea of three-dimensional graphing. If you see something that looks one-dimensional or two-dimension, just plot it and then stretch it in whatever direction, in the direction of the variable that's missing, right? X plus y equals 4 was missing z, so I want to stretch it up and down once I sketch that line. Okay, and then the other shape that they focus on for 3 dimensions is we're used to seeing x squared plus y squared equals 25 as a circle. If I throw in a z squared, this now becomes a sphere. A sphere, and the center would be 0. I did okay on my lines, but I'm not very good at drawing circles, at least not on paper. I can do it on the board. When we get back to being in person, I can do a pretty good circle on the board, but not on paper. So I have a little circle template. Okay. So let me put my axes in here. So this is X, Y, Z. That looks like a circle to me still. So if you're trying to sketch a sphere, you can always put like an equator around it. Gives it more of a three-dimensional feel. So my center is the origin. And just like with circles, my radius is not 25, it's the square root of 25, which is 5. So, you could label that as 5. It's hitting here at 5, hitting here at 5. And how do I put this? Maybe I'll squeeze another example in here. as kind of a lead into this one. So you can tell the center of this sphere is 0, 0, 0, because just for the same reason, the center of that circle is 0, 0. And then the way it works with spheres is just like with circles. So if I had, for example, x minus 4 squared plus y plus 3 squared plus z minus 7 squared equals, I don't know, let's say 9. What would the center of this one be? It's what makes each part 0, right? What would make this part 0 if x is 4? What would make this 0? Y being -3, z being 7, and then my radius would be the square root of 9, which is 3. So you can have your center, you'll know what it looks like when your center is not at 0, 0, because it can be written like this, and then you can figure out what the center is. Which leads into this problem. I know this is a sphere because it has x squared, y squared, and z squared all added together. But with these extra terms right here, it's hard to see what the center is. So in order to do that, what I need to do is make this look more like this. But we want to make it look like this. Just say it, write it as I say. Make it look like this right here, because then it's easy to see the center and the radius. And this you've done this before. What I'm going to be doing to make it look like that is complete the square. So I'm going to group my x terms together. So I have x squared. I'm going to move the 8x next to it. I'm going to complete the square. I'll do that in a second. So we'll leave a blank there. Then I'm going to gather my y terms, y squared minus 6y plus something, z squared plus 2z plus something. And then actually with a sphere, you kind of want all your numbers by themselves. You want them over on the other side. So I'm going to move the 17 over, -17. Here, and I'm going to put, this means we're going to complete yeah. And so we've done this before, right? If I do, how do I figure out what number goes in this spot? I do 8 divided by 2. I did my coefficient and squared, and that gives me 4 squared is 16. I take -6 divided by 2, square that. That's -3 squared is 9. And then finally, 2 divided by 2 squared is just 1. And then when you add the 16, 9, and 1 to the left side, you have to make sure you do the same thing on the right side. And then if you factor what's left over, x squared plus 8x plus 16 factors into x plus 4 squared. This factors into y minus 3 squared. Z plus 1 squared. And then what is this? -16, 17 plus 16 is -1. -1, well, plus 1 is 0 plus 9. So this is going to equal 9. So my center is going to be -4, 3, -1. And my radius is square root of 9, which is 3. I want to make sure I touch a little bit on vectors, or I want to try to. I'm trying not to go too fast here, but because things are moving pretty quickly now. We have, what is it, 3 more weeks left. She did 2 sections on Wednesday, so you know she might be moving at a pretty quick pace. We got to kind of try to keep up a little bit. And vectors, is there a way you do your like hand up or whatever, or like green? Yes. How many people have worked a little bit with vectors in a previous class, maybe a physics class? How many people have some experience with that? I see one. Tiny bit. Okay. Couple. All right. It's okay if you haven't ever seen vectors before. We're not going to assume any pre-knowledge here. And actually, if you've seen vectors before, you might have to change things up a bit. If you've taken vectors before, you may be used to like I, J, and K, stuff like that. But in the 17 book, because of how we're going to express vectors in 17C with actually it's going to look like a matrix. We're going to write our vectors with like brackets like this. Okay. This is also the same. Okay. Just for you folks who have some experience, this is the same as, I could write that as 3i hat plus 4j hat, or I know this is how we do it in the 21 series. We use these kind of brackets, 3, 4. That's how we do it in 21. But in 17, we write them like with closed brackets. And all a vector is an arrow, essentially, when you graph it, but an arrow that has a certain direction to it and a certain magnitude. And I think Professor Burke might have used the same analogy. Like my pen has a certain length to it. And if I place my pen, like let's say at that angle right there, that pen has a certain length. And if I put some axes in, right, like X and Y, it's pointing in a certain direction, like northeast. Okay. But if I move my pen, if I move it around, it still has the same length and it still has the same orientation. So I can plot vectors wherever I want to. So the most logical place to put a vector, if you were going to plot it, would be to put the tail, put my pen at the origin and have it going like that. And what this is telling me, this is like your X component, this is your Y component. So it's like basically going to the point 3, 4. 1, 2, 3. 1, 2, 3, 4. The point 3, 4 is right here. But the vector is just like the hypotenuse. It's just going like this. This is vector A. So you put a little arrow over it. The book drives me nuts when they want to do a vector. They don't do the arrow. They just boldface it. They make it like a really dark printed A. Well, it's kind of hard to boldface when you're writing, right? You can do that with a typewriter, but you can't do that when you're writing something. So we're going to put arrows on ours to really denote that it's a vector. Now it has direction inherently, right? Just because we can tell it's pointing in a certain angle, right? From it. So it has a direction already. But let's talk about the length of a vector we refer to as magnitude. Magnitude. And to find the magnitude of a vector, it's really easy, especially for 2D. It's just like asking you, what's the length of this hypotenuse, right? And how would you do that? Just the Pythagorean theorem, right? If this is 3, this is 4, you would go 3 squared plus 4 squared equals this length. So then this would be the square root of that. So and magnitude, I know we're used to seeing absolute value that makes a number positive, but if you know you have a vector on the inside, we don't mean make it positive. That's just notation now for magnitude. Find the length of that vector. So for us, it's just going to be the square root of 3 squared plus 4 squared, which is 9 plus 16, 25. Square root of that is 5. Okay. Let's do a different vector. Now, you could just be given a vector. In some cases, you might have to come up with your own vector. Here they're saying they want to find a vector, an arrow, that takes me from the point A, 2, 1, to point B, 6, -1. So they're asking for this vector. That's vector AB. We'll call that AB. I could have also asked for a vector from B to A, and we would call that BA with a arrow over it, but they want AB here. And it's really easy to figure that out, because if you think of a vector, you just need to know basically to get from here to here, how much do you need to move in the X direction? How much do you need to move in the Y direction? Okay, and there's a couple ways to think about it. In fact, the way I usually think about it is just like I said, to get from here to here, if my X value is 2 and I want to get to 6, I can already tell I'm going to have to add 4. And to get from a Y value of 1 to a Y value of -1, I'm going to have to go -2. So I usually just ask myself, how do I get from here to here? The more standard way to figure out what vector AB is to take, if you think of this as your initial point, and this is your final point, is to go final minus initial, 6 minus 2, -1 minus 1. I'll put that in. Final minus initial. That's how you get each of these points. Or do it the way I said before. Just ask yourself, how do you get from there to there? So vector AB would be 4, -2. Let's find the magnitude of AB. Magnitude's just the Pythagorean theorem. That's 16 plus 4, so I end up getting root 20. I suppose that's, since 20 is really 4 times 5, the 4 can come out as a 2, so it's 2 root 5. And then something you're going to be doing a lot of in the world of vectors, oftentimes what we want is we want a vector to be a unit vector. What unit vector means is we want the magnitude to equal 1 unit. Here's the way I like to think about it. Okay, root 20 is 4 point something, right? Because root 25 is 5. I always think of it this way. If say you're giving somebody directions, right? And you're right here and someone says, can you tell me how to get to this point here? You point your finger this way, right? Towards this point. You don't need to have an arrow that's almost 5 units long. You just need a little 1 unit arrow, right? That's what a unit vector is. It's just a 1 unit vector is just length 1 that's in the correct direction. Okay. And it's very easy to make something a unit vector. Is we already know vector AB is pointing in the right direction. We just need to shorten it up. So if I simply just divide each of these points by its magnitude, I'm going to get a unit vector. So to find a unit vector, it's always going to be this. In this case, it's going to be AB divided by the magnitude of AB. So that looks like 4 -2 divided by, we'll say 2 root 5. And what you can do is you can actually divide that into both of them. So this could be thought of as 4 over 2 root 5, -2 over 2 root 5. I guess I should simplify that, which is 2 over root 5, -1 over root 5. Don't worry, you don't have to rationalize. You don't have to get rid of the square root of 5 in the denominator. So here's what's true. This vector, while it looks messier, that is a vector that is 1 unit long that is still pointing in the same direction as AB. And looks like we're running. Maybe I'll close with this one. We'll get into adding vectors on Monday. But the reason, this gives some reason, why do we want to make things a unit vector? Let's say in reality, what I really want is a vector that is in the same direction here, but only has length, let's say 3. Okay. Remember, this whole entire length right here was the square root of 20. We've now shortened it down so it's length 1, but now I want it to be length 3. So what the process is this. We take a vector, we make it a unit vector, and now if I want it to be length 3, I'll just multiply this vector by 3. I'll multiply my unit vector by 3. That's kind of like stretching it out, so it's 3 units long. So I'll put here, multiply my unit vector by 3, because I already know that's going in the same direction, and by multiplying it by 3, it's gonna give me magnitude is going to be 3. So it's 3 times 2 root 5 negative 1 over root 5. And with constants, we haven't talked about this, you've talked about in class, you can literally just distribute it. So it's going to be 6 over root 5 negative 3 over root 5. Yeah, we better wait. Here we go. Wait. If you got a couple of minutes, I know I'm late, but I was going to talk about adding and subtracting vectors, but here's a nice exercise that I really like. This was a problem in the book that I think really just gets directly to the idea of adding vectors. So I'm skipping a problem here, but that's okay. How we add vectors. Let's say you have this weird shape here, quadrilateral with a couple of diagonals, and we've got some of these vertices labeled here. So go ahead and sketch that out. And this, I think the best way to show you how to add vectors is to just see it on here. Okay, when we add vectors, this is how it works. If I have, so PT, I might have to draw multiple diagrams here. PT would be a vector that starts at P and goes to T. So that's like right here. There's PT. If I want to add the vector TQ, notice TQ is already right there to there. So the tail of T goes like this and takes me to Q. Okay. It's kind of just like, you know, if you took this path to get from P to Q, if you went from P to T and then from T to Q, what would that be the same as a single trip? Do you see that would be the same as just starting at P and going to Q? PT plus TQ would be the same as the vector PQ. The way we add vectors is tail to head. If you go this one and then you throw this vector on, that's the same as just starting here and winding up there. Let's try these next two and then we'll be done here. What about QR plus RS? Try that and see, let's type in the chat, what single vector would that leave you? Would that be the same as if I did QR plus RS? Nice. Yeah. Yeah, so it's really easy, right? QR goes from here to here. RS goes from there to there. If I add this vector plus this vector, that's the same as just going directly there. That's equal to QS. And one more, what is ST plus TQ? Oh, that one's a little bit trickier. Yeah. If you went ST and then added TQ as a single vector, that's just like going from S to Q. So that would equal just SQ. Okay. Good. The one thing we haven't talked about is how you subtract vectors, but we can do that on Monday. Do that on Monday. You guys are tired. You've had a test.